Today, we'll talk about finding the area under a graphical curve. Work is given as a force exerted over a distance. Graphically, we commonly plot force with respect to distance. When the force is constant over the displacement it is exerted, we can simply multiply force times distance. This is equivalent to length times width on the graph, giving the area. When the force varies, though, we need to approximate the area in between the curve and the x-axis. We can do this by drawing shapes underneath the curve, finding their areas, and then adding them together to get one total area. In this example, we have a plotted force-distance curve. The force is not constant, so we can't simply multiply force times distance. So we'll need to find the area under the curve through a different mean. We can recognize that this graph is a triangle. Recall the formula for the area of a triangle, 1/2 base times height. Here we recognize from the graph that the base is 6 meters and the height is 3 newtons. Multiplying out, we find that we have 9 newton meters, which is equivalently 9 joules of work. In a different example, our curve is not a straight line. It is truly curved, so we'll need to approximate using a different method. In cases like this, it often helps to draw shapes in between the curve and the axes, like so. We can start with a rectangle, and then add 2 triangles to fill in the remaining gap. The area of each of these figures is trivial, so we can calculate each of the areas and then add them up at the end to find our approximation of the total work. For the rectangle, we simply multiply the base, which is 1.5, by the height, which is 4. This yields 6 joules. For the triangle on top, we recognize that we have a height of 2, being 6 minus 4, and a width, or base, of 1.5. Multiplying these by 1/2, we get 1.5 joules. For the final triangle, we take 4, being the height, and then multiply that by the width, 2.5 minus 1.5, which of course simplifies down to 1. Multiplying out, this triangle gives 2 joules. With all of our quantities, we can now add them together to get our total work of 9.5 joules. Here we have a slightly more complex example, a graph which you might see in a problem dealing with impulse. It's slightly less convenient here to draw polygons, and they will not necessarily be a very good approximation of the graph. So instead, we'll draw grid lines, and then count the boxes in between the curve and the x-axis. Not all of the boxes under the curve, though, are whole. Sometimes there are partial boxes. You can look at partial boxes and try and guess about how much of a box they contain. In the first example, each of the 2 partial boxes shown is about 1/2 of a box, so we can add them to get 1 full box. In the second example, each of the boxes is partial as well, and we can add them to approximate 1 entire box. Counting the boxes requires you to take note of the scale on the axes of the graph. Because our drawn grid lines are 1 unit apart on the x and y axes, we have 1 newton by 1 second for each box. I've counted roughly 90 boxes, so multiplying 90 boxes times 1 newton second per box gives 90 newton seconds of impulse.